in this lesson of mechanics, which is the second lesson on forces, we're going to have a look at forces as vectors. We've learned a little bit about vectors in pure. And we're also going to have a look at applying forces to situations with trailers involved as well. So just a quick recap of vectors. We can add them together like this, and they work in exactly the way that you would expect. So this is going to be 1, 12 would be the resultant vector here. And this one would be minus 8, 12. Okay, just to remind you that you can add them and you can multiply them by a scalar as well. We can also write them like this. So vector A is 7i minus 2j. And hopefully you recall that I is the horizontal unit vector and j is the vertical unit vector. So I could rewrite this as 7 minus 2, which would mean 7 across and then 2 downwards. So overall we are going in this direction. Okay. Now to find the magnitude and direction of vector A, we need to remember what those two terms mean. The magnitude of A, which I could write like this, this just means the overall length or the size of vector A. So it's gone 7 across and 2 down. So using Pythagoras, I can find this length here. So that's 7 squared plus 2 squared square rooted. So that's 49 plus 4, which is 53. So root 53. I don't think that simplifies, does it? No, just root 53. To find the direction of it, I've already drawn a diagram explaining what sort of direction it's actually moving in. If I draw in some axes, just the x and y axes, we need to describe this angle in here. Okay, and then we could give an angle below the horizontal. So to find this angle, which I've called theta, I'm going to do inverse tan because I've got the opposite and the adjacent. So inverse tan of opposite over adjacent. So inverse tan of 2/7. And if I do that, I get 15.9 degrees. And we should state where we're actually measuring that from. So it's 15.9 degrees below. I'm actually going to write below the vector I because that's the horizontal unit vector. I could also describe it as a bearing, perhaps, if I measured it from north. If I measured it from north, which would be up here, then that would be 90 degrees plus this angle. So plus 90, that would be 105.9. That would be as a bearing. Okay, so you do need to be specific about where you're measuring from. Now I'm going to talk a little bit about how we can use vectors to help us in mechanics problems. Okay, so it says a resultant force of 3I plus 8j newtons acts on a particle of 0.5 kilograms. So here we haven't just got a force that's left or right, we've got a force that's at an angle. There's 3 newtons to the right and 8 newtons up. And it's acting on a particle of 0.5 kilograms. And we've got to try and find the acceleration. So you've been given a force, a mass, and we want to find an acceleration. So hopefully what you should be thinking about is the equation F equals ma. Force is mass times acceleration. And in here we can actually substitute vectors into this equation. Because force can be a vector, because force can have direction. So I'm just going to underline that. So I'm writing it as a vector. And the same with acceleration, that can have direction too. So these two can be vectors. Mass, however, is just a scalar because it doesn't matter if, like, we can't really have 0.5 kilos left or right, it's just 0.5 kilos. So we can substitute these vectors straight in. I'm going to write it as a column vector. So 3/8 for the force equals 0.5 times the acceleration, which I'm just going to call a. That's what I've got to find. So what I'd have to do here for my next step is divide both sides by 0.5. So that's same as timesing by 2. So it's going to be 6 and 16 would be vector A. Okay. And it asks for it in the form pi plus qj. So that would be 6i plus 16j. And the units would be meters per second squared because it's acceleration. Okay. Find the magnitude and bearing of the acceleration of the particle. So remember that A was 6, 16. I always think it helps to draw a diagram. So it goes 6 across and 16 up. So overall it is doing that. So the magnitude is going to be 6 squared plus 16 squared square rooted. So that's 2 root 73, or as a decimal, it's about 17 if we round it. So that's 17 meters per second squared. And the direction it's asked us to do it as a bearing, so it needs to be measured from north. Okay, so it needs to be measured from here. I'm going to work out this angle in here first of all, though, and then I can do 90 minus this angle to find the bearing, which would be in here. So theta is going to be inverse tan of opposite over adjacent. Which is 69.4 degrees. Okay, so the bearing would be 90 minus that. So 20.6 degrees. Okay, so there we go. So the important thing here is just that force and acceleration can both be vectors, and you can actually substitute those vectors straight into your equation, which is quite handy. Okay, here's another one. So we've got 3 forces here. Force 1 is 2, 4. Force 2 is minus 5, 4. And the third force is 6i minus 5j. So we've got these 3 forces all acting in different directions on a particle of mass 3 kilograms. Find the acceleration of the particle. Well, the total force is just going to be the sum of these forces. And because they're already written as vectors, the directions are already handled already. So I can just sum up 2, 4 plus minus 5, 4 plus 6 minus 5. And that will give me the total force. And I can still use F equals ma. So I can set this equal to 3 times a. So on the left, if I add this up, 2 minus 5 plus 6 is 3. 4 plus 4 minus 5 is also 3. Okay, so you get to there. I can divide it by 3. Okay, and that would be our answer. So the acceleration is 1 meters per second squared. Or we could write that as just I plus j meters per second squared. Or I suppose you could work out its magnitude and direction, but if it just asks what is the acceleration, then we should probably just leave it as a vector. Okay, here's another example. So a boat is modelled as a particle of 60 kilograms, and it's acted on by 3 forces, similar to our last question. Given that the boat is accelerating at a rate of 0.8 minus 1.5 meters per second squared, find the values of P and Q. So let's write down these 3 forces first of all. We can still use F equals ma. So I've got 80, 50 plus 10p, 20q plus minus 75, 100. So that's the sum of all my forces as vectors equals ma. So that's going to be 60 times, now I told me the acceleration is 0.8 minus 1.5. Okay, and now I can work out as much as I can. So I'm going to combine all these things on the left. So I'm going to have, so it's going to be 10p plus 5. And down here we're going to have 150 plus 20q. On the right, I can multiply these, so 60 times 0.8 is 48. And 60 times minus 1.5, so it's minus 90. Okay, so now I've got this equation. I've got to try and find what P and Q are. We can just consider this as 2 equations. So we've got the top row, and then we've got the bottom row. Okay, so if we just look at the top row, 10p plus 5 equals 48. So P is going to be 48 minus 5 divided by 10, which is 4.3. On the bottom, we've got 150 plus 20q equals minus 90. And we can solve that to get minus 12. Okay, and those will be our two answers. So we can treat the top and bottom of these vectors like an equation, and we can just do it as a pair of equations. It's sort of like just having two equations written in one. What we're also doing here is we're basically considering if we've got a particle like this and we've got different forces on it. So maybe we've got one over here, one over that way, one over that way. What we're basically doing, and we'll do more of this when we do the year 2 mechanics, is splitting up these forces into their components, into their horizontal and vertical components. Like this. I've split them all up into horizontal and vertical components, and then I'm either considering the total horizontal or I'm considering the total vertical. So this top row, which is looking at the horizontal direction, I'm basically saying this arrow plus this arrow minus this arrow is what I'm doing there. And then when I look at the bottom row of my equation, I'm considering all the vertical bits. So that bit, and that bit. That's basically what we're doing. And we will come back to things that look a bit more like this later on in the mechanics course. Okay, to practice some questions on vectors, I'd suggest you have a look at exercise 10D. I've put here, feel free to start at about question 5 because some of them are quite basic. Okay. Okay, the next thing I want to look at is on trailers, or more generally, we can call this connected particles. So anything where we've got two particles or more connected by a string or like a tow bar, something that's connecting these two objects. Okay. And the classic example to look at is a car towing a caravan. That's in the picture here. Okay. I picked that picture because it's of Cheddar Gorge, not far away, I think. So I've got a very basic diagram of the car and the trailer down here. So I've just got a box representing the car, and I've written its mass, and a box representing the trailer with its mass, and then a line between them which represents the tow bar. Okay. Now, there's some other things we've been given in this question. The force on the engine of the car is 1,000 newtons. So I can draw that on. So we've got a force going this way of 1,000 newtons. The resistance on the car is 200 newtons. So this would be things like friction with the road, air resistance, things like that. So I'm going to label that as 200 newtons. And that goes the opposite direction because it's a resistance. The resistance on the trailer is 150 newtons. Okay. Now we've got to find the acceleration and find the tension in the tow bar. Okay. So the acceleration, bearing in mind that these two particles are connected, okay, and assuming that it is what we would refer to as an inextensible tow bar, or you might say an inextensible string, although I hope they're not tied together as string. If they're inextensible, then this means the two objects accelerate at the same rate. Okay, as the car accelerates, the caravan is going to accelerate at the same rate. They will move off exactly the same. If it was extensible, so imagine it was like an elastic band, then when the car moves, there'd be a delay before the trailer moved, and it might move at a different rate. But if we assume it's inextensible, then they will accelerate at the same rate. So that means that this whole system, both objects, accelerate at rate A. Okay. Now, what I'm going to do here is I'm going to consider the whole system as one big object, basically, because they're connected, so I can do that. So if I consider the whole system, then I've got 1,000 newtons to the right, so I'm going to resolve to the right as my positive direction. So 1,000 newtons minus 200 newtons minus 150 newtons. The only other forces on here, there is some forces in the tow bar here, which I'm going to talk about in a minute. But for now, we'll leave it as this. So these are my forces, and then this equals ma for F equals ma. The total mass is 1,300 for the whole system times A. And now I can solve this equation. So 1,000 minus 200 minus 150 divided by 1,300. So A is 0.5 meters per second squared. Okay, so I found that by considering the whole system. Now I also just said about there's some other forces involved here in the tow bar. Okay, there's a tension in the tow bar. Now, first of all, imagine that you are perhaps sat in the trailer or sat in the caravan. If you're accelerating to the right, there must be a force pulling you along. Otherwise, how would you be moving to the right? The trailer doesn't have an engine. So there must be a force pulling you to the right. Okay, the trailer feels like it's being pulled along. So we have a tension here of T. If we now consider we're sat in the car, if you are the car and you've just had a caravan hooked up to you, that caravan is definitely going to feel like it's pulling you back. And maybe you've towed something yourself before. It definitely feels like your car is being pulled back by this big trailer or caravan behind you. So from the car's perspective, there's a force T going in this direction. Okay. And that might look odd having these two opposing forces, but that is true. That is the tension in the tow bar. If I was going to include those in this equation here that I just did, well, this one on the left would be plus t because it goes to the right, and this one would be minus t. So they sort of cancel each other out when I consider the whole system. Now what I'm going to do to find out what t is I'm going to consider the objects separately. So I'm just going to draw a dashed line down here. If I consider just the trailer, okay, so I'm just looking at the left half of this diagram now. I'm still going to resolve to the right. So I've got T is the force pulling it to the right, minus 150 equals 300 times the acceleration, which is 0.5. And then I can solve this to find T. So 300 times 0.5 plus 150. That's 300 newtons. Okay. If we now do the same process but from the car's perspective, we should end up with the same result because they're both T. So from the car's perspective, again, I'm going to resolve to the right. I've got 1,000 newtons to the right, minus 200, and it's going to be a minus T because the T is pulling back. Remember, the caravan is tugging back on the car. So that's minus T. Then that equals MA. So for the car, that's 1,000 times 0.5 was A. Solve this to find T. 1,000 times 0.5 plus 200 minus 1,000. Yes, T is then 300 newtons. Okay. So that's the general strategy in these trailer type questions, is you can consider the whole system, so all of the objects together, or you consider them individually. And as long as you resolve accurately, you will get a consistent set of results and solutions. Okay, here's one for you to do. Similar sort of question. Maybe have a read of the question. I've given you a diagram here to help you too, and see if you can answer it, and then I will go through it. Okay, so in this example, we're just given two particles. It doesn't say actually what these objects are. Of masses 5 and 3, and one's called P and one's called Q. They're connected by a light inextensible string. Particle P is pulled by a horizontal force of magnitude 40, so let's put that on the diagram, along a rough horizontal plane. Particle P experiences a frictional force of 10 newtons, so you can fill that in. And particle Q experiences a frictional force of 6 newtons. Oh, actually, I've labelled my diagram the wrong way around. So P is being pulled forwards by 40. That's better, isn't it? By 40, resistive force of 10, and Q has got a resistive force of 6. That's better. Find the acceleration of the particles. So because they are connected, I can assume that they accelerate at the same rate this way. Okay, that's why it's being pulled, so it's going to go that way. So you've got to find the acceleration and find the tension. We can put the tension on now. Same sort of thinking as the car and the caravan. The trailer, which in this case is Q, is being pulled along to the left, so there must be a force pulling it left. P is feeling like it's being sort of held back by Q, so there is a force this way of T. Let's do the whole system. So I'm going to resolve to the left this time, just because that's the way that I've modelled it as moving. You could have your diagram facing the other way, so it's all sort of reflected the other way. But here I'll have 40 minus 10 minus 6. I could write minus t and plus t, but obviously I don't necessarily need to do that. And that equals the total mass, which is 8 times the acceleration a. So my acceleration is 3 meters per second squared. Now to find the tension, I'm going to just look at P first of all. I'll do it for both and we'll check I'll get the same answer. So for object P, going towards the left, I've got 40 minus 10 minus T equals 5 times 3, because I'm just looking at the left-hand side of this diagram. So I get T equals 15. 40 minus 10 minus 15. There we go. We do the same for Q. We'll resolve to the left. I've got T minus 6 equals 3 times A, which was 3. So that's just 9 plus 6, which is 15. Okay, so our answers agree. It is worth doing it both ways to check you get the same answer. It's a nice easy check to do. So there we go. Part C, explain how the modelling assumptions that the string is light and inextensible have been used. So the inextensible bit first, that's to do with it not being stretchy, so that means that they will accelerate off at the same rate. The fact that it is light means that we don't have to consider the mass of the string. Okay, when we say light, that actually means it has no mass, not just that it doesn't weigh very much. It means that we don't have to worry about the string's mass at all. Obviously, in real life, if it was a piece of string, you would expect it to maybe form this sort of shape, which would affect its motion as well. But we're not worrying about its mass, so that makes things easier. Okay, I've got the same example as we had before with the car and the caravan, but I now want to think about what happens when the car slams on the brakes. How does that change the forces involved? So everything else is going to stay the same, except the car is no longer having a force on the engine. So perhaps they've spotted a hazard ahead and they've come off the accelerator and put their foot on the brake pedal. So there's no more force on the engine, and instead they've put their foot on the brakes, and there's now a braking force. So that would be something that goes this way of 690 newtons. The resistance on the car is still 200. So I'll put that in. And the resistance on the trailer is still 150. Okay, we can also put T on in a moment as well. Now, let's do the acceleration first of all. So I'm still going to model it as accelerating to the right with A. However, you might already realize that this A is going to come out as negative because we are decelerating. Put the brakes on, so overall you're slowing down. So I'm expecting my answer for A to be negative if I model it in this direction. If I modeled it left, then obviously it would be positive. So if we consider the whole system again, and I'm going to do to the right, because it's still moving to the right, even though its acceleration is technically to the left, but I'm still going to go left to right. So I'd have minus 690, minus 200, minus 150 equals the total mass times A. So I've got minus 690, minus 200, minus 150 divided by 1300. So A is minus 0.8. Okay, so what I expected to happen has happened. We've got a negative, which is good. It's slowing down. Okay. Now to find the tension in the tow bar, in this case it's actually called a compression, we need to think a bit more carefully. Before, when it was accelerating to the right, we said the trailer was being pulled along by the car, which I suppose is still true, but it's not being dragged along, so it's not accelerating anymore. Okay. If you were sat in the trailer or the caravan now, and the car that you were attached to slammed on the brakes, you would feel like you were being pushed back. You'd feel like you're being forced to slow down by the car. So T now actually goes this way, which is the opposite direction to where it went before. Okay, so imagine you're sat in that caravan, the car that you're attached to slams on the brakes, you're going to feel like you're getting pushed back. It's trying to slow you down. If we now think about what happens from the car's perspective, if you're driving along in your car and you slam on the brakes and you've got a massive heavy caravan behind you, it's going to feel a bit like the caravan wants to keep going and the caravan wants to basically try and crush your car. So the force the other way is T in that direction. And this is the reverse of what we had before. Okay. When the forces look like this, which they did when it was accelerating to the right, we call this a tension in the tow bar. When they go the other way, like I've just drawn, so I'm going to write here accelerating, and this one's braking, then we call this a compression. Okay. Now, let's consider how we actually work out T. We're going to use the same method as before. So with the trailer, I'm going to cut my diagram in half again, and I'm going to resolve to the right. I've got minus T minus 150 equals its mass, which is 300, times the acceleration to the right, which is minus 0.8. So let's work out what this is. So we get 90 newtons. I suppose we could resolve it the other way if we wanted to. If we resolved left, we'd have 150 plus T equals 300 times 0.8, and you'd still get the same answer. So you can resolve either way, as long as you're accurate. If we do it for the car, I'm going to resolve to the right. I've got minus 690 minus 200 plus T, because T is going to the right, equals 1,000 times the acceleration, which is minus 0.8 to the right. If I solve that, let's just check. We still get 90 newtons. Okay, there we go. So be careful when you get a question about braking. It's quite a common exam question that comes up actually, because you have to understand that the forces in the tow bar are reversed to what happens normally with a trailer. Okay, questions I'd like you to do on this, exercise 10E in the book, are all about connected particles. But I'd like you to not worry about question 4 for now, which I think is about lifts, because that's what we're actually going to cover in the next lesson. Okay, but you can answer all the questions apart from number 4 in that exercise.